so learning outcome 7. First of all, we need to introduce the idea of what we mean background radiation is. So background radiation, So background radiation which is always present and doesn't come from a particular source. So we're talking about, when we brought the sources into the classroom, but this radiation was here before we did that. In the UK, the majority of background radiation comes from natural sources. Of this radon gas, is the most common, and the radon gas comes from the Earth itself and spreads out into the atmosphere. And other natural sources include rock, soil, and because we use rocks for buildings themselves, cosmic rays, which come from outer space, so the remains of events which have taken place in space. And lastly, the food and drink which we consume can contain small amounts of natural radiation. Meaning that our bodies themselves actually are radioactive. There's radioactive carbon, for instance, within your body, potassium. Artificial background radiation comes mostly from medical uses. So there is a benefit there. Okay, so number 8 is the idea is that radiation can cause harm to living cells. And I'm not really defining yet what I mean by smaller levels. We'll go into that. Right. So for example, getting small levels of radiation, although it might not instantly do anything to a living creature, in the longer term it can increase the risk of, for example, cancer or other diseases as well. Because basically the radiation can interfere with the chemical signals which take place within a cell. So if you start changing those chemical signals, then you change the instructions, remember, that the cell gives out, right? The nucleus of a cell gives out to the rest of the cell to do its job. If you start interfering with those instructions, then the cell might stop doing its job properly. Okay? Now this is particularly important for young people, which is why the law that under 16s are not allowed to use radioactive sources, which is why I have to demonstrate them. Right? Because the younger you are, your body's still developing, your cells are still changing a lot. Okay? And therefore they're more at risk to kind of those instructions getting interfered with. Okay? So younger people are more affected by exposure to radiation. Larger levels of radiation though, right, can so alter the nature of a cell that they kill it outright, basically. So that's the kind of two main risks. You've got the kind of small level, long-term risk, high level, short-term, and your kind of immediate damage. So for this reason, it is important that we measure levels of radiation. And compare to background levels. That our bodies are used to. Okay, so that's the kind of the descriptive part of what we're doing. And now we kind of come to the definitions. Now I'm going to kind of mix together 9 and 10. I think it makes a bit more sense. So the first one is an equation. So D is defined as absorbed dose. And it's measured in grays, capital G, small y. And I'm putting a wee bit more with this one. So it's defined as the energy absorbed per kilogram of material. So that's what that equation says. If you take the amount of energy, E, divide by the mass, the number of kilograms, you'll work out how much energy you're getting per kilogram. So E is the energy absorbed. And energy, if you remember, is measured in joules. M is the mass affected in kilograms. So we define another formula, capital H, right, which we're just about to define, is equivalent dose, equals capital D, the absorbed dose we've just defined, multiplied by, and this is a WR, a W with a wee subscript R, So it's not two separate letters. Do you know what I mean by a subscript? Okay, so a small r kind of slightly below the line. And it's a small w as well, just to be clear on that. So H is equivalent dose. And it's measured in sieverts, capital S, small v. And once again, we're going to give that a kind of wee bit more detail. We're going to give it a definition. And this is more the kind of statistical sort of idea. Right? It's a measure of the biological risk of harm associated with an exposure to radiation. It depends on the absorbed dose, quite obviously, because that's in the formula. The part of the body affected. And the type of radiation. So all of these can alter the risk. So D is our absorbed dose that we've just defined. It's measured in grays. And WR is known as the radiation weighting factor. And it's quite unusual in physics. It doesn't actually have any units. It's a dimensionless number. And basically what it says is that, for instance, alpha radiation, if you're exposed to it, causes 10 times as much risk as beta or gamma. So we would say the radiation weighting factor for alpha is 10, whereas for beta and gamma it's 1. So it's really, that's how we take account of the different types of radiation, by putting in that multiplier. It's just a number that indicates risk. So example, during a medical investigation, a patient's liver of mass, let's see, it'll be reasonable, 0.8 kilograms, is exposed to 0.5 millijoules of alpha radiation. So I said that full joules is quite, a full joule of radiation would be an extreme amount of radiation. Calculate the absorbed dose and equivalent dose. Oops. Misspelt those. So usual problem solving. What do I know? In the question I'm told the mass is 0.8 kilograms. The energy is 0.5 millijoules. And when we get prefixes, remember, try and substitute for them at the point where you're listing your variables. So 0.5 millijoules is 0.5 times 10 to the minus 3 joules. And then the first thing we're asked is equivalent dose, absorbed dose, and then we're asked equivalent dose. So we've got two question marks here, D equals question mark, H equals question mark. So the first equation we'll use to get the absorbed dose, D equals E over M, 0.5 times 10 to the minus 3 divided by 0.8. Get your calculator out. And it's 6.25 times 10 to the minus 4, and the units of absorbed dose are grey. The equivalent dose is H equals dWr. We've got D, we've just worked that out. WR will generally, either it will be mentioned in the question, or you can go and look up a table in the data sheet in the exam. Okay, so page 2 of the exam is a data sheet where it will tell you what radiation weighting factors are for the types of radiation involved. So you go and check for alpha radiation, the radiation weighting factor is 10. So substituting in, and the units are sieverts, right? Capital S, small v. So kind of final answers to these two questions. Right, D is 6.25 times 10 to the minus 4 grays, and H is 6.25 times 10 to the minus 3 sieverts.